So now that you've had a chance to see how Java futures work visually, let's actually take a look at how they can be programmed. And this will be similar to what you just saw visually, but it'll kind of fill in some of the pieces and show actual Java code. And as before, we're going to use this example to multiply big fractions concurrently using Java futures and the Java the Java common thread pool, common fork join thread pool. We're going to show this example in the context of something called the BigFraction class. I like to use this example because it can be used to burn a lot of CPU time while still doing something plausibly useful. The BigFraction class supports arbitrary precision fractions that uses big integers for the numerator and the denominator. Recall that a big integer is an arbitrary precision integer, so a big fraction is just an arbitrary precision fraction with arbitrary precision numerators and denominators. There's a couple different factory methods to make fractions. One of them can make so-called reduced fractions. So for example, if you say 44/55, that's reduced to 4/5. If you say 12/24, that's reduced to 1/2. 144 2/16, that's reduced to 2/3, and so on. That's one thing you can do. You can also have factory methods to create non-reduced fractions and then subsequently reduce them. And because reduction could take some time, you might want to do the reduction in the background, which is why we don't just always reduce them when we create them. Because that way we can make them very quickly and then use concurrency to reduce them without taking away the processing of the calling thread. You can also do arbitrary precision fraction arithmetic. So you could say 18/4 times 2/3, which will yield 3. And of course, you can do all kinds of other stuff. It gets a lot more interesting the bigger the big fractions are, because it's not always so obvious what the results are. And sometimes they can be rather ridiculously large, as we'll see when we look at some examples. And something else you can do here is you can create a so-called mixed fraction from an improper fraction. I don't know why they came up with the word improper fraction. It sounds kind of like it's broken or something like that. But 18/4 is an improper fraction. And you can have a method to convert that into a mixed fraction, which would be 4 1/2. So that's the mixed version of an improper fraction. I guess that makes it proper. Maybe it wears like a tuxedo or something like that. So let's talk about how we could actually write a little program using Java futures to do some operations on big fractions. And this will illustrate the use of futures in conjunction with the callable functional interface, which we've talked about a couple times before, which comes from Java 5, and the common fork join pool, which comes from Java 7. None of the stuff here, as you might expect, is part of the modern Java features, but this is the history, the foundation of where we got to as a way to work around some of the quirks with what we're about to talk about. So in this particular case, we're going to define ourselves a callable task, which is going to return a result via a single method that takes no arguments directly. We can pass them in as the effectively final variables in a lambda expression, which is what we're going to do here. And this is a two-way call. So computations are given to it, vat parameters, and it returns a result, which will be a big fraction, or specifically a future to a big fraction. And you can see here that we have, these are the strings, these are the fraction, numerator, and denominator. And Java enables the initialization of this callable via a supplier lambda. And supplier lambdas are just one example of a mechanism for providing, this is actually combining modern Java functional programming features with traditional Java concurrency features. You can see that we're using these so-called effectively final variables. Effectively final variables are just a fancy way of saying if a variable is assigned and not changed up to the point where it's used, it's effectively final, even though it's not in fact marked as final. And why this is important is you can't pass non-final or non-effectively final variables into lambda expressions in modern Java. You can only have final or effectively final variables there. If you can read this link to find out more about what an effectively final variable is. We then turn around and submit this task, the callable, to the common fork join pool, and that will then go ahead and run in the background in one of the threads in the common fork join pool. And you can see that the side effect of calling submit on the common fork join pool is we get back a future to a big fraction. And that big fraction future will trigger at some point after the computation is finished. Now, that of course raises the question, what do you do in the meantime? If the only thing you do is turn right around and call get on the future, you might as well have just had a two-way call, because that's effectively what you're doing. So more likely, you're going to do something else here. You can, like I said, you could go off and check to see if the user has provided any input. You could invoke some more asynchronous computations that would run in the background. That has a whole can of worms associated with it, but at least you could do that if you chose. So something is going on here. We're not going to say what that is at this point, but something else is happening. And then at some point, the calling thread says, all right, time's up. I need that result. Can't make any further progress without getting the result. So it can go ahead and call the get method on the future, which will then wait for the result, which could either be success or failure. You might get back the result, which would be a big fraction, or if something horrible happened, like you tried to create a big fraction that was multiplying by 0, or dividing by 0, then you'd end up getting some kind of exception back. And as I said before, you can also wait a certain amount of time. So that's the end of the quick overview of showing how to program with Java futures in practice. And you can see it's not particularly hard, but there's a set of problems we're about to talk about, some limitations with this approach.